Uh, Welcome everyone to the ESIP Cloud Computing session for March 28th, 2022. And we are excited to welcome Alex Merose, I believe software engineer at Google, right? And you've been working on Apache Beam for geospatial, and I believe you also have some affiliation with the Pangeo Forge project. Do you want to give a little introduction, actually, briefly, before we do announcements?
Sure. Yeah, that covers a lot of it. I was going to introduce myself in the presentation, but yeah, I'm a software engineer at Google. I work in Google Research. I work on nowcasting and weather infrastructure at Google, and I'm a contributor to Pangeo Forge.
Cool. So yeah, I think we're all excited to learn a little bit more about Apache Beam in a minute, but then let's just do some announcements. So I think maybe Annie or Jim, do you want to talk about the ESIP summer meeting?
Sure, I have never been to an ESIP meeting in person, but we are having an in-person meeting in Pittsburgh. I'll go ahead and drop the link for the telecom notes in there again. So registration is open. So breakout sessions our proposals are due April 29th. And I'm excited to find me some Amish food because my dad lives in that area and I miss it. So you'll find me at the Reading Terminal Market at some point. And I'm really excited to meet you all in person.
Is that like a lot of really fresh cream and eggs?
It's so good.
Yeah.
I'm gonna have to bring a cooler and hopefully they'll let me fly back with it.
Nice. Cool. All right, any other announcements from the group? All right, awesome. Well, why don't you take it away, Alex?
Thanks. I'll share my screen. Can everyone see my title slide?
I've got it in front of me now.
Yep.
Great. Well, thank you everybody for having me here. I'm here to talk about Apache Beam for geospatial data. I've introduced myself already, but I'm a SWE at Google Research. I've also contributed to this software package called Weather Tools. And the last thing I didn't mention in my introduction is that I'm new to geosciences. Although I work in this area now, I come more from a traditional software engineering background, just as a caveat. I'd like to say that, start off the talk kind of focusing on the problem at hand, which is that geospatial data, you can think of as the original big data. Definitely preaching to the choir here, but even up till today, we produce so much geospatial data from a wide range of sensor technologies. It's produced faster than we can process it, and most of this data is thrown away. At least that seems to be the case, given the kind of like weather meteorological space that I work in. And yet, there's so much huge potential to use these imaging technologies to make a critical difference for scientific impact and commercial interest. That is, if we can make use of the information in a reasonable amount of time. With that as a framing of the problem, we might enter Apache Beam. So to offer a brief history, in 2004, Google published a paper on MapReduce, which totally changed the game and how distributed processing is done. And the idea is to break down problems into these embarrassingly parallel components to be processed to these two large steps where you just focus on kind of like the code at hand. You don't have to worry about fault tolerance or the actual infrastructure that you're deploying on. Kind of the history of Beam, more or less, is that Google would publish, build internal infrastructure like MapReduce and release these papers. And then there'd be these parallel chains of development. Google would have like a single infrastructure for its data processing, and they'd release papers while they focus on core algorithms. And at the same time, the open community would, the open source community would read these papers and create their own implementations. And you see that with MapReduce and Apache Hadoop. And then you have like many years from 2004 all the way to the 2010s of this kind of research at Google, and then research outside of Google and open community development big data tools. Around 2014, Google kind of combined all its learnings into this data flow programming model that it created a cloud service for. And then a few years later in 2016, it released Apache Beam as kind of like this unified framework that I'll talk about in a second. Apache Beam kind of took all these learnings and Google donated it to the Apache Foundation to kind of reconcile the two different parallel tracks of development. And yeah, now I'd like to talk a bit about why Apache Beam as opposed to all the other big data processing tools that are out there. I would argue Apache Beam is a really great choice because it's a really high-level API for distributed processing. Instead of being a framework itself, it's much more like, it's much more like an API for frameworks or general way to describe kind of any generic amount of big data processing in the ilk of MapReduce. In its unified model, it supports both batch and streaming operations. And you'll see in a second, I'll provide an example of like, it does require minimal code change to go from a batch job to a streaming. A really great thing about Apache Beam is that you basically choose your own adventure. You can choose the language in which you write programs. It can be, natively, I think it's in Java or C++. You also can write it in Go or Python. You can choose the SDK in which you're running and developing on. It could be Apache Think, which is more oriented towards streaming jobs, or Apache Spark, which kind of does a bit of everything. You can use a proprietary service like a Cloud Dataflow, or maybe I think AWS Kinesis is very similar. And you can choose the execution environment. If you wanted to roll your own environment, you could run it on a Kubernetes cluster. It's possible in theory to run it on like Dask and the Hadoop file system or things like that. So that's kind of the idea of the kind of open and really pluggable API. And last, it's open source and under really active development from the community, which is a great reason to use Apache Beam. But like, I don't know if I've kind of talked a lot about Apache Beam. I would like to dive in and more in depth into like, what problem it's trying to solve and how it's trying to solve it. And to do that, I'll use a motivating example that's talked a lot about in, big data type frameworks. So enter Wordcount. This is somewhat of like the hello world of MapReduce or these big data frameworks. And the problem is something like this. Given a large corpus of text, how do you count the frequency of each word that occurs? And this is like, let's say the problem you're trying to do is create like an n-gram model, and you'd like to get the base of that, you need your prior distribution. If I was going to write this in like, conventional, like, undergrad level programming, it'll be a single program for a single machine, and it might look something like this, where I get a, dictionary of words to number of words, and I go through all the words in this large corpus of text, and when that word appears, I increment it by 1. Now, I'll ask, how would I split this work across 1,000 machines? That's more or less it requires somewhat of a shift in mindset, and that's where these frameworks like Apache Beam come in. One thing you might one tip that I would recommend is you would like to eliminate global state. So this shared state of counts and incrementing you really would like to get rid of. And ideally for parallelizing tasks, you prefer to use pure functions at every step of the way. So let's kind of take a look at like the original MapReduce framing of this problem, how it addresses it. So you have this large corpus of data, and the first step you would like to do is divide up the data into different chunks that you might handle to different machines to parallelize, to hand out. For each chunk of data on its own machine, you provide a map function. And this explains how to transform each element into to do it for the aggregation, to make it lend itself for a parallel amount of processing. Machines will process the chunks independently. And then there's this shuffle phase where based on the type of element that you're doing, you send it to the correct machine. And then the machine that it's on, it'll do a reduce operation. It'll aggregate based on the type of data that it is. And you can aggregate the work to get the total result of each component part. And then in the final step, you kind of output or produce the overall results. This is a really powerful generic framework. You can basically, refactor any sort of problem into a map in a reduced step. It requires some distortion beyond recognition maybe, but that is more or less the idea behind how you might parallelize the task. And for word count, it actually might look something like this. So this word count is a really good fit for MapReduce. I would like just to note that Beam, while it can do MapReduce, it's a lot more general. It can really perform arbitrary operations on graphs. Kind of a technical problem with Beam, with MapReduce is that like often it required, if you use Hadoop, you'll know this, that it requires a lot of waiting for previous stages to complete before computing the next stage. Beam is much more like Spark in that it will, through deferred operations, it'll kind of compute things more smart and more fast. I would like to say that like this mindset shift is still pretty consistent in this new programming model. Now that we kind of understand the high-level approach, I would like to explain more in depth about how this would manifest in lines of code. And to do this, I need to introduce some core Beam programming concepts. So, beams are made of pipelines, and it's just pure Python. And this is what a pipeline looks like in Python. You have with Beam, pipeline as pipeline, and then you define your pipeline in this block. This usually is in like the run or the main function with arg parsing in a Python program. This pipeline object, you can pass configurations to define the environment in which it runs, but by default, it just runs on a direct runner, which is just your local machine, your workstation and multiple threads. Pipelines, there are two components that define a pipeline. There are P collections and P transforms, and this is a simple definition of a pipeline. So a P collection here is in red. These are, P collections is short for the P and P collection and P transform are parallel. A P collection is a parallel data structure that doesn't actually hold data right here in this machine. It defines like it's a placeholder for a graph of operations that depending on the execution environment can like be really heavily optimized. I think in most of the cases of the environments where a Beam is run, a P collection handles all the abstraction of like when to serialize the data to persist it onto disk, or whether or not it should be kept into memory. All the shuffling operations are kind of abstracted for you in the framework. Really, you just need to think about the data, the shape of the data as it exists in the graph, as well as what transformations you do on the data. And the transformations are these P transforms. And there's a lot of different types of transformations, which I'll talk about in a little bit. But here, I've listed two of them. Here you have this kind of unique one, which creates an initial data set in memory. And this is just two strings to files of like, let's say weather data. And then all we do here is just print them out in parallel on a direct runner. So this actually is a valid Beam program. If you put this in a Python file and ran it, it would do what you would expect. And this is basically the fundamentals of what a Beam pipeline is. It is a graph of operations that also takes data into account, not just tasks like maybe Dask or other sorts of parallel systems. Just for clarity, because you'll see examples in a little bit, instead of variables that hold P collections, it's more traditional to keep on using this pipe syntax that you see here. So you have a pipeline, and then from there, that's like the root of all operations. You can have many branches from the root. Then you kind of pipe, P collections into transformations, and you have just a series of operations. Usually you'd like to, these are kind of anonymous in some sense. They're unlabeled. It's also often common to label the different steps in a pipeline. So this syntax here, this overloaded pipe, like a binary shift operator, along with the overloaded pipe operator, is kind of the normal flow of pipeline definitions that you see in Beam programs. The rest of it, though, like you can see, print is just normal Python, and in the create, there's just normal Python data structure, just a list. Pretty much everything else in Beam is just pure Python, usually just expressed as methods or functions. So I would like to take a step back and talk about the different types of operations in Beam. You could say there are three different general categories. There are element-wise operators, which are similar to like the map, but the fundamental core operation in an element-wise operator is parallel do or par do. And these are things that take in an individual element and reduce either a single element or a list of elements. And usually there are a bunch of sugar on top of that. there are transforms that aggregate, and there are different types of aggregation. Sometimes you want to aggregate while applying an operation like summing. Sometimes you just want to do kind of what we talked about at the top with the MapReduce example, where you want to control kind of like the shuffle and like where data ends up onto a single machine. Usually those are group by keys, which I'll kind of get into in a little bit. But in general, this is where you take a large series of examples and you kind of combine them into one thing, more or less. The last category is, they're called composite transforms, and generally you can define your own transformations in Apache Beam, and those are made of other element-wise and aggregate examples, or transforms. Basically, you can define your own subgraphs of operations and have them be single transformations, and these are used all the time. This lets you really succinctly express like kind of a high-level set of transformations on your data flow graph. And with that, I would like to maybe talk about, show some code about how word count actually exists in a valid Beam program. And this is pretty much the same thing we saw in the high-level diagram of MapReduce, but expressed in, more canonical Beam. So, here we read from text. We split every line of text into multiple words with this regular expression. We map them into the word and one token. The combined Burke key is this aggregation step that also applies a sum, an operation. Then we map them into strings of the frequency and word count, and we output to a file. And from the perspective of the type of transformations, this outlines several. So like Beam has first-class capability for I/O, and these are the special type of transforms that do side effects. Everything just, as mentioned, Beam is pure Python. Although you really want to structure things in terms of pure functions, you totally can do any sort of side effect that you would like within a function. And these composite transforms, they do a lot of side effectual things. All of these different operations are different expressions of a parallel do, and there's a lot of sugar on top of it to express things at a higher level, like flat map, which maps a single element to multiple, or a map which just applies a function to a single element at a time. And then there are combining functions, or combining transforms, and this is a special type of combiner that not only associates things by key, and in this case, the key is the word and the value is the number. This will, shuffle all of the different keys to their own different worker machines, and then also apply the sum operation, which is expressed very succinctly right here, as opposed to, a group by key in a map, which I'll show an example of later. Yeah, and that's a word count in an Apache Beam program, and this is a kind of a high-level expression. You see here that there are lambdas, and these also could be really, like tens or hundreds of line Python functions, as long as they fit within the program. So let's say for a moment that the requirements have changed for the end user. You want to perform word count, but now instead of doing a batch set of texts like historical examples, now you want to, let's say, do word count, like get the frequency counts for incoming streams of data. Let's say you have a Twitter stream that you're subscribing to, and you want to see within batches of time, like what the frequency count is for maybe a live Bayesian inference model. The pipeline would actually be mostly the same. There are a few adjustments that you would need to make. So for one, the I/O, you just shift the I/O from one type to another, and these forms of I/O, there are also I/O connectors, but they have streaming support. The very top reads from a publish subscribe system, or PubSub, which is just like an Apache Kafka stream. I think it's just a GCP service. And then suddenly you have streaming I/O capabilities. The difference, though, is that now you have this type of Beam operation called window into. So like if you were following it, one thing to note is that it doesn't really make much sense to aggregate across an element stream. It really is simple to like apply a element-wise operation to an infinite stream. You can do that one by one, but to aggregate, you need to do it over, you need to know the whole size of the data up front. To do that, what you need to introduce is the idea of windowing, which means you kind of group batches of incoming data into stuff of, but by timestamp into fixed windows of stuff. So here, this operation says basically like a non-overlapping windows of 2 minutes is when you want to make batches of different aggregations for your word count. This is a different type of combiner called a group by key, and this is kind of what I was mentioning before. This is like the traditional MapReduce step where you shuffle the different keys, which are in this case I think are they're words, the X and that lambda. You put those to their own machines, and what this produces more or less is a single, each machine will have a single data structure that's a tuple, which is the key, and a list of the values of the tuple, which in this case are a list of numbers. And then, you have the normal operations that are all parallel dues. And the parallel dues, not all of them are shown here, but they more or less sum all of the list of values and then output the results. And in this case, they write to a database like BigQuery. That's a overall introduction to Apache Beam. Just to summarize, like kind of Apache Beam in general, but a lot of benefits to this distributed approach. It is really tuned to turning problems that you have at hand into embarrassingly parallel tasks. And this is really essential for highly scalability. Beam offers a lot of simple data processing abstractions so that you can focus on what you want to do. And you don't have to worry about how to parallelize it, like what hardware it's running on, or how to make it fault tolerant, as long as the operations are idempotent and they can be processed out of order, you can trust that they'll be executed and executed efficiently and correctly. It's really nice to have an upfront graph of all operations and data because it lends itself to optimization. You can element-wise operations, even combine operations can be, scaled out infinitely to threads and processes or virtual machines. And having the whole graph defined at once, including the data, lets you define opportunities for operator fusion, which I think is definitely a huge speed up. Pretty much all the element-wise operations and many of the reduce operations, they can be fused together into basically one function call on the virtual machine. And Apache Beam is really great. This approach is great because you have a unified model for batch and streaming. If your requirements change and you need to shift from one model to the other, it ultimately requires little code change. And the abstraction for the code change really is oriented around, lets you just totally specify the requirement of how that will shift. Now that we've kind of established in the mindset of Apache Beam and this MapReduce model of programming, I would like to focus on its application to geospatial data. Specifically, I would like to focus on a library called Xray Beam, which is created by Stefan Hoyer, and I've contributed to as well. The short name is called Xbeam. Xray, I think, is maybe one of the standards, not the standard, for manipulating geospatial data. It's really it's like an in-memory format of the NetCDF model, which is like the Unidata standard. And I would like to talk about how, I'd like to keep the word count example in mind as we shift towards how it can be applied to Xray and geospatial data. And the shift in mindset and the shift in how we structure programs is very similar. So let's talk about the overall approach of Xray Beam. So let's say we have a data set. This is the diagram on the far left, and it's just this really huge thing that let's say is exabyte or petabyte scale. It is definitely too big to fit on a single machine and disk, let alone RAM. And it might require lots of machines to work with. Kind of the mental model we have with Dask, just as a comparison, is that you would define a chunk ahead of time, and you would operate it. A chunk is defining kind of the limits of what is available in RAM, and you would basically apply the operations you would write normal like scientific Python code, and it would really smartly kind of like load things into a graph of tasks and kind of load memory in once and apply it in these really large tensors as element-wise operations that were mapped or parallelized, which is really excellent. And that's kind of how it operates. And I kind of see this as, it's definitely a different parallelization strategy, and a really valid one. The model that Apache Beam makes is more similar to Wordcount, where you split up the original data set into smaller types of data sets, Xray data sets that then could be distributed across VMs or workers in the same way that you would in a traditional MapReduce model or in Beam. And then you apply the processing onto workers, and then you have like a similar type of reduce operation that combines the results and then fuses them all together. And So let's talk about maybe what the library does at core, or like the components of it. Um, Kind of like into just to say, Xray Beam is just a library that kind of adapts Xray to Apache Beam. And kind of the way it works is that the mindset you now that you're familiar with Beam is that everything is a P collection of data sets instead of one large data set, and that's how it's broken up. It definitely is a much lower level tool. And ultimately what it does is it solves the problem of how do you represent distributed Xray data sets. So we offer components to break up data into variables and chunks. And you can see in this code example, this is more or less how it's done. Key is defined in two components. There's an offset, which is the offset from the origin of the Xray data set. And then there's variables that let you define what variables are included in each of the chunks. And if it's none, it's assumed to say that you can include all variables. And in this way, with this kind of placeholder or this mechanism, you have a way to like keep track of a data set out of order, yet maintain its structure and how it's distributed. So just as a example, this will come up often, is that as you manipulate data sets, you need to update this housekeeping data structure, and you can do it in this pure functional way where you kind of you have these mutator functions instead of updating the data structure, where you can replace variables or offsets, and then you can also add additional offsets. So this is how you might write sample data in Xray Beam, and all this is doing is it's creating the housekeeping structure and defining the offsets and the key. It's creating a data, it's creating sample data, which is I think just a whole number of, it's like the 2 times the offsets in a large shape, and creating 2 different fields, foo and bar, and outputting it. The thing I really want to emphasize here is that again, to underscore the P collections that you're working with, ultimately, the housekeeping you need to keep track of are keys and data sets, X-Beam keys and Xray data sets. And that's the mental model you have to keep when doing processing. And then the rest of it is just a Beam pipeline. And this is very simple, very similar to the original example I produced up front. And in fact, you can, instead of defining all the transformations like in a data set kind of abstraction you might see in Spark, we actually just delegate all that processing to Beam as a framework itself. Because you have the mental model of P collections as X-Beam keys and data sets, you can then use any sort of function like this way of mapping tuples of stuff. It just unpacks the arguments and do everything that you want just with pure Python primitives and just inserting them to Beam as a framework. So this will I think take the averages across all the dimensions. It'll average across Y, the Y dimension offset, and produce and kind of remove that offset dimension in all the keys. And it'll do it in a really highly parallel way. It'll be split up based on whatever crate records, how it splits up the data. So now that I've explained more or less the paradigm of Beam and how its application to this type of working with this data, I would like to give a more practical example. Let's say we have a ZAR Era 5 data set of surface level, and we want to calculate some climatology on it. How can we do this with Xray Beam? And let's say this is, maybe like a petabyte of surface level data as Xray. If you go all the way back to 1950, let alone 1978 or 1979 to the present, Era 5 surface level data can get really large. So this is the entire program. I've actually omitted some of it, but you open an Xray, you open a ZAR data set, and you defer the execution of it. You define, excuse me. I'll walk through the pipeline kind of in steps. More or less, you take the reference to the ZAR data set as opposed to the actual data, and you split it into chunks, and you define how it's chunked. So here, you're opening it and distributing it to Xray, X-Beam chunks. So like this is the I/O component. Ultimately, you're reading from chunks in one ZAR and writing to ZAR chunks. And it is the standard data model, the P collections. X-Beam offers the ability to further split chunks into smaller amounts. So it offers the capability to split into smaller chunks and also to consolidate chunks. That actually has full support of rechunker if you want to just do the split and consolidate steps all at once. If you want to totally restructure a large data set. Instead of defining an operation within XBeam as a framework, we delegate to map tuple. And what this more or less does, I've omitted this function from the slide, but this extends the data set to have a month and an hour as like 2 dimensions of the data set. And then we have actually within the framework the ability to per the key, which again is this key that keeps track of the offsets and the variables. It just sums across all the dimensions of that key. This is there are a few combiners within XBeam that this is again a composite function that does a lot of the group by top operations and applying the operations like sum. And this was like an average as opposed to just a simple sum. And then here we write the output to ZAR. And it will, because it has knowledge of all the offsets and counts, it can just write the metadata once based on a template, and then in parallel write the output ZAR. I will note, given that I just mentioned the template, it is possible for the framework to calculate the template ahead of time. However, it's far more efficient to define the template in the program itself. So at the top of the thing I've omitted in this one slide, you from the source data set, you can redefine the template using just normal Xray operations. Here, this just expands the dimensions to accommodate the transformation that's happening in this rekey chunk on hour operation. That's very similar. Just taking a step back about Xray Beam. Xray Beam is a library that is an adapter between Beam and Xray and makes sure they play well with each other. Something that I guess that implies is that you get the best both worlds of Dask, total, single machine utilization with the single thread scheduler, and the best of Beam, which allows you to farm out work across like an auto scaling number of virtual machines. What's really great is that all this is pure Python, and you can bring whatever tool that you want into any method or program that you write. So you can bring every tool that you want for geospatial data to perform arbitrary computation. And while you're not expressing things in terms of pure operations on data structures, so there's a loss of flexibility. For this change in mindset, you get high scalability by using Apache Beam. And it's even scalable to the point of if this Era 5 data, if we shifted it to, let's say, ECMWF's real-time forecasts, and we applied the same climatology thing, similar to the word count example, we could take climatology of forecasts, although I'm not sure that makes sense. I mean, I guess, there probably is a more domain-specific appropriate task. Like if we wanted to make a machine learning model to have our own like post-processing of forecast combined with several other data sources, ECMWF and maybe others, we could do that in a Beam pipeline that would be very similar to our offline or batch analysis. Yeah, so that's my talk. Thank you very much for listening all this way. I hope you got something out of it. And from here on out, I'll answer any questions, and I would love to have a discussion. Thank you very much.
Hey, Alex, that was super cool. It seems like it's really like I got our HPC cluster. We often submit like a bunch of jobs to like job array, and each one of those job array jobs is like using Dask to like process some subset of files and then inserting them into the ZAR data set. It's like that's the same workflow, right? Like, but we could use, it seems like we could use, instead of just using the kind of clunky Slurm job array thing, this would allow us to kind of standardize that workflow, right? With and would it work on? So is there what's the thing that actually scales out Beam? What do you call those things? Or maybe I missed that in the beginning because I joined a little bit late. But
I guess maybe it could be like the SDK that you choose. So you can choose the infrastructures, maybe like whatever you represent your HPC on. Like maybe if you can get, for instance, like Apache Spark to run on HPC, which is also open source, and there are systems to install it. Yeah,
Okay.
you could run Beam on Spark.
Okay. And then we could take that that same paradigm to the cloud then also, obviously, then like you're showing with the ERA 5. Yeah.
Right.
Cool.
Yeah, totally. And like,
Yeah.
might even make sense. I mean, what's really great is you could port the same code to run on your own, roll your own like data center or HPC system, and then you
Yeah.
could take it to any cloud provider. I mean, like at least the big three that I'm familiar with, they all offer services that Beam can run on. Like often cloud providers in general, you can like go to Databricks and use a managed Spark cluster and run a Beam pipeline on it.
Right. What's the one for AWS? It's something else, right?
I think I said Kinesis before, but I think it might be Elastic MapReduce.
Okay. Okay. And it also, it's cool that you've integrated rechunker, because that's one of the awkward parts of our like HPC workflows, that the way, if you just use the rechunker as it exists, you have to write out as our data set and then read it back in just to insert it in into the master ZAR data set. Yeah.
Right. Yeah. Yeah. Totally. And that's, yeah, really critical. And it also is kind of difficult to split up into a bunch of parallel work. I mean, I think at one point in time, rechunker itself had a Beam executor on top of it, like when you deployed on it. And I think it also worked on Dask. I think Xray Beam is really nice because it is like even more of a generalization. It's not just Beam for rechunker. It's just Beam, or it's Beam for Xray in general.
Yeah. Cool.
Yeah, so I'm trying to understand how the executors work exactly. So I would guess, I'm sorry, I'm most familiar with Amazon Web Services. So I believe like you can run Apache Spark on Elastic MapReduce, right, in AWS, and that's basically how you would get this on that particular cloud provider. So I would assume, yeah, Google Cloud Dataflow is similar. I'm not familiar with some of these other ones, but okay.
Something to keep in mind, and I can share my screen and pull up some links. So the executor, the type of executor in Beam, the language is called a runner, and that's the thing that runs the pipeline. Depending on the implementation you choose, whether it's Spark or Think or Dataflow, they have different capabilities. Apache Beam, if you go to its website, it has a capability matrix. And what it means is that, to implement a Beam runner, there are like 4 or so key operations that need to be done. And I've talked about them at a high level, but different runners have different capabilities and will support certain types of computation. Like, for instance, like Think, I don't know, some may have all the operations, but only for batch and not streaming, whereas some might be more streaming oriented, but not have all of the operations. And I can show the capabilities matrix if people are interested.
Yeah,
thanks, Rich.
You could talk it through.
This looks like a great reference. Thanks, Rich. Okay, Kinesis is powered by Think. Okay, I was trying to look this up earlier and I couldn't find that, but yes, Kinesis is more streaming oriented and it's much more like Apache Think, whereas I think Elastic MapReduce is much more like Apache Spark. So the capabilities matrix that you find on the Apache Beam website will, that's like your shorthand for looking up, what the trade-offs are for which infrastructure you'd like to use in AWS or another cloud.
So right now, Beam is, you feel like, I mean, I assume Beam is mostly in the Google space, but maybe like Kubernetes will will take over the, yeah.
Well, so I was wondering about this kind of a basic framework question, but it seems to me like we're talking about frameworks for doing distributed analysis on something that can be like well structured into these n-dimensional arrays, which fit into this Apache Beam, Xray Beam model, but Kubernetes is more generic version of that, where you could have an arbitrary container that's less specific to like an n-dimensional array structure of data, right? You just have an in and an out. So I was wondering if anybody else on the call has a good way of like articulating the different use cases into basically like very generic like batch processing with a black box container versus, you know, a large data set that's already been, you know, structured and in its n-dimensional chunks. Or if you think that Apache Beam could be used to handle the former use case, if it's well articulated into MapReduce operations, what do you think?
If no one wants to jump in, I have like a thought on this too, but I'll wait. Like at least I have a lot of experience with GCP's Dataflow. And I think ultimately it runs on Kubernetes under the hood. And what's really great about that is that with Apache Beam, you can define your own, you can actually run your own container for the underlying environment. So like, you know, I'm sure, I don't know if anyone's worked with a lot of ECMWF stuff before, but like sometimes you want to run MetView on like a worker instance, and that can be kind of a bear. And like a very simple way to do it is just to use ECMWF's Docker container they provide that has MetView on it, and just install Apache Beam on it. And then you can basically totally control your environment. And within a single pipeline, if you have, you know, some, let's say like, you know, people in a different side of an organization that program in a different language, you can actually have multi-language environment similar to how you would in like, you know, orchestrating a lot of you know, Kubernetes type clusters and like a microservice model. I think Beam is just really great because it provides a really succinct, you know, abstraction layer or like API for expressing computation. And yeah, I think you're right, Amy, is that it really is that is kind of the trade-off. You have to use this API, but you're afforded so much.
Right. Yeah, I'm just thinking like what level of control do you have over your environment within Apache Beam implementation? Like if you're running it on EMR, then you might, I have to remember, actually, it's been a while since I worked with EMR, but how you would specify your environment that you need to run the different pipeline steps in. But yeah, that's probably like a executor specific requirement, like figuring that out probably, right?
Right. Yeah, and I believe they have like Apache Beam has a lot of documentation, I think, on running it in a bunch of different runners. And like they can help you, you know, supply the specific arguments to configure the environment that you want. And you can do that in a Python program. Basically, you just pass those into the pipeline object in that context manager that I demonstrated in the slides at the top.
So can you say, maybe if you can say, how is Google using Apache Beam right now in practice?
I feel like Google runs on Apache Beam.
Oh, really? Wow.
Yeah, they like
so all of its search algorithms are running on Apache Beam now and stuff, or?
I can't
Okay.
I don't know about search because that's not what I work on. I'm not totally sure, but it is like a pretty fundamental infrastructure for Google to do both streaming and batch operations. And kind of in general at Google, you know, it is a company really centered around automation, and Apache Beam totally fits that model where you don't think about how many resources you need to solve a problem or how to scale it out. You just define what the data looks like and how much data needs to be processed. And then Beam as a framework, let's say GCP's Dataflow, it auto scales. It like gives you the appropriate amount of resources that's, you know, to process it as fast as possible and as compute efficient, as like cost efficient as possible. And that's true for a lot of internal infrastructure, and Beam, I feel like, is a really good showcase for it.
Oh, I'll go ahead and ask the new guy question. Is this what's underneath Google Earth Engine? That's probably the most familiar platform I'm used to, but
Definitely a lot of components use Earth Engine. Use Apache Beam. It is like definitely a workhorse at Google. I don't know. I think in terms of like, so admittedly, I don't have too much experience with Earth Engine, and I think they actually have more of like a different sort of system to process certain requests. It might be more like a traditional server model, but definitely for batch operations and like other large scale data management, they use an internal version of Beam, which is I think called Flume.
I can definitely see some of the parallels. So it's nice to see the kind of a little bit under the hood, even though I have no idea what I'm looking at.
Cool.
Do you guys, Alex, do you have examples of maybe using Xray Beam, some simple examples for geospatial applications that would run on Google Colab or something like that?
Yeah, actually the Xray Beam project, there's a good read the docs, and it has, it is a Colab read the docs set up. So it has, I actually don't think all of it is there. If I go on GitHub, Beam, there are a few code examples.
Mm-hmm.
And like one is the climatology example that I presented, and the other is rechunking. And I think there could be more examples contributed or developed over time, but I think this is a really good start to talk about what kind of can be done. And I think the use case is really like if you want to do analysis on data sets that are really, really large, and you want to kind of do an analysis on the whole data set, Xray Beam is a really good fit. Because you do need to like really get the most efficiency out of your parallelization. You really do need to think upfront in terms of the compute graph. So like the low level of abstraction is really beneficial to actually get optimal results, as opposed to thinking more in terms of like the scientific manipulation.
So I'm wondering too, like we've been using QHub, which is an open source project that uses Terraform to deploy Kubernetes with Jupyter Hub and Dask, on various cloud providers. Or could you imagine something like that would, be set up for like these big Beam pipelines where you just deploy whatever, deploy all the required infrastructure on some provider and run your pipeline and then shut everything down?
Yeah, I think that totally would work. In fact, I owe Ryan Abernathy a write-up and explanation kind of justifying this, but that's kind of what I hope happens to PangeoForge.
Yeah, yeah, that would be awesome.
The mind shift, the kind of like the scalability over flexibility is the big thing, where it's like Dask is really great because it requires minimal code change to get a high level of parallelism. Apache Beam requires more. It requires that you change how you write programs to be parallelizable. But like you do get a big benefit from it, because then instead of like having the fact that it's a graph that includes data and tasks as opposed to tasks is pretty important to that, because then I think the infrastructure PangeoForge uses right now is oriented around, it's much more like Apache Airflow, if you've ever used that. It's much more oriented around doing things in a sequence in like a DAG. But this is with Apache Beam or let's say Spark, you actually are capable of doing things in a streaming fashion and doing them like really performantly and quickly, but it requires that you take into account what the structure of the data is at every stage of the pipeline.
Yeah, which totally makes sense for like PangeoForge, right? Yeah, very well established steps.
PangeoForge, but I'm also now it's making me also wonder how Apache Beam may or may not be used for some of the once data's already in ZAR, right? Like you already gave this example of R5, like what's the value add of Apache Beam versus just using the typical like Dask data frame for your data? Yeah, do you have a thoughts about that, Alex?
There's a really good section that compares, like in the Dask documentation, that compares Dask versus Spark, and Spark is really the closest thing to Beam.
Right.
And like, it does talk about like when you'd use one versus the other, but like the very last section I really like, which is like just use both, like Dask and Spark, and similar Dask and Beam can be just used together. So that's one type of approach of like when you choose one, A, B, or A and B. Another type of approach is, another way to kind of more directly answer your question is, if you're like Dask, I have an appendix that I never actually created a slide for, but it was like kind of like the optimizations to make Dask run really performantly, you kind of get in the default of Apache Beam. Like I remember reading the best practices section of the Dask docs, and it was saying like, consider fusing operators, or, control the size of your graphs, based on the data and things like that. And a lot of the stuff you get up front, like it kind of like how do I say this? It requires you to do extra work to change how you write your program, but the extra work actually is the thing that will make your program way more optimal.
Well, and sometimes like it seems like, when Dask just works, it's awesome. And when Dask doesn't work, it's making like the wrong decisions about like how to do things. And you're trying to like force it to do the right thing and everything. And just, it does seem like at that point, like, okay, I know what I need. I know what I want this to, like, I know what the operation should be like, and it's not making that you're trying to tell it, no, don't, make just these decisions. It seems like at that point you'd be like, okay, yeah, let's just use Beam, and because we know what we know what the parallelization should be as we go along through this workflow.
Yeah, it's kind of like that's exactly right, because you do write a graph yourself as opposed to Dask, where you like it creates a graph, an implicit graph.
Right. So remember that like the Dask developers workshop, like just before COVID, last in-person things, like somebody from Capital One or something was showing like an editor, like a Dask, graph editor or something. And everybody's like, ooh, I want that, or something, it's like kind of like, but it's just kind of funny because it's like the opposite, you start high level and then you want to go in and to kind of try to get it back to lower level. And this is like the other way, right? Lower level. So yeah, the two together. Yeah. That seems like super powerful. Yeah.
Right. Yeah. Xray Beam, especially, it is, I think like, I mean, it also includes Xray, but it is like Dask on Beam is like one way of looking at it.
Yeah.
And I think, as I understand it, Dask is currently having a new scheduler in development that might make it rival with Beam in the first place. We'll see how that kind of shapes out. Whether it is that scheduler is performant enough to, have this, really great level of abstraction where you just write scientific code. But I do think that at a certain point, for certain concerns of scalability, you really do want upfront explicit control.
So in another session, I'm thinking also about planning for the summer session, but in another session, I think it would be nice to talk about like all the options that are out there and when you might want to use one versus the other for distributed analysis and distributed processing, because they're, like we said, like there's a lot of these things that are complementary, and maybe, yeah, couch it in some actual use cases, of course, would be good. So that could be a good summer session, but also it could just be a knowledge sharing session if we can structure it properly.
Yeah, happy to. Do you think that might be in person? It'd be nice to have a post-COVID type conference type thing.
Yeah, so ESIP summer session, for those who weren't here at the beginning too, Jim mentioned how it's going to be in person in Pittsburgh, July 19th to the 22nd. So yeah, I'm looking forward to seeing everybody again, I hope. It is at the same time as as other things, but it's unavoidable, you know? So hopefully as many people can be there as possible. It'd be cool to see you there.
Yeah.
Any other questions for Alex?
I'll ask two really low-hanging fruit. Do you have a link to your slides that we can throw in the notes? And then I see you've got a couple of examples here, but is there kind of a code book, or is there an idea for a recipe to help some of those who are definitely a little lower on the skill ceiling here?
You know, I would love to like develop more. I think that would be a really great way to expand this to, you know, like the help on the documentation side, which is pretty critical. I'm curious, maybe we could discuss offline too. What kind of things would you like to compute? Like something I'm less, you know, I don't really use Dask, for instance, so I don't understand like where it struggles. And I think maybe, or, you know, like those would be really good motivating cases to write examples in Beam, or even just the standard workflows in Dask, and then porting them to Beam would be really helpful for me to know, just to show like maybe as more of like a Rosetta between the parallel frameworks. So
I don't know if
yeah,
that's
if you'd
something
like
the
to
cloud
work
computing
together.
cluster. Yeah.
What's that?
I don't know if that's something the cloud computing cluster would like to help with, but I would certainly be interested in at least trying my hand at that.
Cool. Yeah, we're open to contributions. That would be awesome.
Yeah, it's definitely come up before, like how do we consolidate documentation, like, or this idea of an Earth Data Cloud cookbook. Is that kind of also what you're talking about, Jim?
Yeah, I know it's kind of like trying to nail down a flying carpet, but
Exactly.
a nice landing spot is always a welcome entry point.
Well, I think example notebooks are always helpful, right? Especially if they're like well declared in terms of environments and how to reproduce things and stuff like that. Yeah, I'm very inspired to contribute to existing resources like the NASA OpenScapes Earth Data Cloud Cookbook, but I definitely think that that's something that ESIP Cloud Computing Cluster members can help out with, and I'm interested in different ideas on how we should do that.
Yeah, that would be so awesome. Yeah, because this is really, really generic, and I just am limited to the examples that I am familiar with. Yeah, I'm really excited to work on that. I think that's a good, you know, action item or next step for where we are with this project.
Totally. I think that this has definitely come up before, where I'd love to have more working sessions where we like work on like all the notebooks that are out there, like try them ourselves, see what errors we run into and like fix them, and just like have like a working session where we do stuff like that, you know, would be really cool.
Cool.
All right, so we're just about at the top of the hour. Any other last thoughts or questions? All right, thanks so much, Alex. Really appreciate your time. I'm happy that we recorded this so we can share it out with the wider group. I think there's a lot of other folks who would be interested to hear about this recording after the fact. So thanks, everyone.
Thanks,
Thank
Amy.
you for the opportunity to share.
Bye.